Hello, folks. Welcome to our introduction to Raymarching. This is a tutorial series put together by my students. I challenged two of my students to put together some Raymarching introduction tutorial materials, largely written. And they had about 5 weeks. They had no graphics background. They had no background in integral or multivariable calculus or linear algebra. And so they had to pick up all of those tools and deliver those materials to me. Um, and they did it, and they did pretty well. These are some renders that they made. I think they're pretty cool. What this means is that you can start here too. Hopefully, this video will give you some of the tools to understand ray marching and to be able to put together some of these things yourself. If you're interested in ray tracing or ray marching, but you're scared of the math or the background that you need to get there, then this tutorial series is for you. When I was examining materials to learn ray marching, one thing that I found is that there was a fair amount of introductory material that kind of taught you what the ideal was, a fair amount of advanced material that helped you like with doing advanced modeling and things like that. But there were less materials that kind of tried to fill the gap. And so that's a little bit of what this tutorial series is trying to do. This tutorial series is about starting from the beginning, even if you don't have a math background, giving you some of those necessary math tools so that you can make some progress. Let's talk about what this tutorial series is not going to teach you. What is some of your prerequisite knowledge? You should have some development experience in your background. The goal of this tutorial series isn't to teach you those things. So if you have a strong foundation in a programming language, you should be capable of kind of following and walking through this code and then picking up GLSL pretty much okay. I find that having a project is a great way to learn a programming language. So if you're interested in ray tracing or ray marching, then this could be a way for you to kind of build some of those chops. But again, that's not going to be the focus of our tutorial series. We'll say things like, hey, we put this in a function, this has a return, and we're just going to move forward. Okay, that's enough of me rambling. Let's let the students take it away, let you get started, and hopefully get you on your way to making some cool stuff, something like this.
Ever wondered how to create complex worlds and beautiful realistic renders like this one with nothing more than simple math? Ray marching is a technique we can use to render complex 3D or 2D scenes with shockingly few lines of code. Despite its power, it is able to run in real time on any old browser. For the sake of this tutorial video series, we're going to be programming on the ShaderToy website in GLSL, a rendering specific close variant of the C coding language. GLSL stands for OpenGL Shading Language. It's a programming language specifically designed to run directly on your graphics processing unit to render at the pixel level. It's free to create a ShaderToy account by going to www.shadertoy.com. Now, let's examine how this algorithm works and compares to the real-world physics and other rendering techniques. You may have heard of photon mapping or ray tracing, where light rays bounce off objects until they hit the camera. So this is the algorithm. A light source will cast out countless rays, some will collide with objects, and if they hit the camera, they'll be rendered appropriately. So this is an example scene. We have a light, an object, and a camera viewer. So the light is going to cast rays off in every direction. And when they hit an object, they're going to reflect off of it. And any rays that hit the camera are colored with the color that they hit, the object that they hit. So let's take a look at that in effect. So here is a light, a viewer, and two objects. The first thing the viewer is going to do is find the nearest object to itself. And this circle is called a signed distance function. They're very cheap to compute computationally. This distance, like I said before, is the largest we can travel without hitting any objects, no matter what direction we travel. So we cast a ray in any direction, and then on the circumference of our circle, we create a point and repeat this process. We locate the nearest object and create a circle of that radius, extend the ray, create a point, and then continue. So eventually when we hit an object like this, we color it on our screen with whatever color the object is here. So because this object was red, we would color the pixel red. If we had instead missed an object, the ray would continue until reaching the maximum number of distance somewhere off the scene. Now that we've established a foundational understanding, let's take a look at this. A program is free to access and can be found on the ShaderToy website, and the link is in the description. So this is simply another example of the ray marching algorithm where the center line represents the current ray being marched. And you can see that as I rotate this around, these circles are changing. So first, what our custom built model will do is locate the nearest object to itself as before, and then this represents that next circle. What our custom built model displays that we before obfuscated was this screen here, which the rays pass through. So this is how a field of view is determined. To determine where exactly on your screen the pixels are colored, a Raymarching algorithm places an invisible two-dimensional screen directly in front of your camera. Whichever pixel the ray passes through on the screen will be colored with whatever the ray eventually hits. In this model, the background color changes to the pixel which would render on the screen by the center Raymarch. Another feature of the FOV is that while increasing its value allows the viewer to see more of the scene, it comes with fisheye distortion. So let's take a look at that in effect. If I place the viewer over here, and I have a very small FOV, and I switch to three-dimensional mode, we can see that the objects look pretty normal. However, if I change the FOV to instead be much greater, so I'll bring the camera much closer so I can see more of the scene, but we're going to get a much worse distortion effect on these spheres. So that's how FOV works. Feel free to try this software for yourself and see how the program is affected when you move the FOV yourself or edit variables such as max iterations in the code. If you desire, play around with it until you get a sense for what the program is doing and how different variables affect the output. Congratulations on making it through the conceptual overview video. Check out the next tutorial in the series. In the next video, we're going to give an overview of vectors and vector functions useful in the later rendering process. See you in the next one.
Okay, so you have the basics of ray marching. The basics of backwards ray tracing, which is what most people mean when they say ray tracing, are basically the same. You have a screen, you fire rays through it. The biggest difference between ray marching and ray tracing is that in ray marching, when you ask the question of like what's closest to me, you're not necessarily hitting something. In a ray tracer, you run intersection tests against all your objects, and so you know if you've hit one of them immediately or not. What I really like about both of them is that you can do them in something like a fragment shader or shader toy and get cool stuff out of them. Okay, so I think hopefully you should be able to describe the basics of ray marching. Where we're going to go next is talk about vectors. So I'll see you again after that.
All right, guys, welcome back to another video. Now that we understand ray marching conceptually, it's time to get into some of the simple mathematics behind it, specifically vectors. Vectors are the fundamental math behind most all visual transformations and ray marches. Additionally, they have many practical applications in other disciplines, such as physics. There are some features common to all vectors, which are essential to building a foundational understanding. So they're used for rays in our ray marching algorithm, where we represent the ray origin and direction as a vec3 vector. Rays are simply vectors with infinite length and magnitude. So they're also used to calculate lightings. Vectors are measured against each other to determine how much light shines on a particular point of an object. And we'll get more into that later. It's also used to move and define object camera positions and transformations. So vectors are fundamental to moving anything in a 3D or 2D space. So here are some features common to all vectors. All vectors have a magnitude, a length, and a direction. So they can point up, down, left, right, and then they have a certain length. So this vector has a length of 5. All vectors additionally have an x and a y component and a z in a three-dimensional space. So for this example, this red vector that has a length of 5 has a y component of -4 and an x component of 3. In GLSL, vec2s take the input of the x and y component to create a vector. So to create this vector, you would put in the y and x components. And this is shown here. For the shown image, vec2 3, -4 would produce this shown vector. Vectors in GLSL can have 2, 3, or even 4 components. For example, vec2 has x and y, a vec3 adds a z component, and a vec4 adds a w, often used for colors or positions in a 3D space with an additional parameter, such as time. So there are some crucial functions to be aware of, but also in GLSL in general. So the normalize function for a vector, to do this, we normalize a vector by maintaining its original direction, but replacing its magnitude with a standard of 1. This is accomplished by dividing the x and y, and potentially z, by the length of the vector. The normalize vector function in GLSL takes a vector as an input and returns a normalized vector as an output. So this is our vector from the last example. A normalized version of it would have a length of 1, an x component of 4 over 5, a y component of 4 over 5 and an x component of 3 over 5. Another important function is the dot product. The dot product is a key way by which we can multiply two vectors together. This is essential for lighting later, so please keep it in mind. In GLSL, the dot product function, dot, and then you put in two normalized vectors, returns the dot product of these two vectors. A dot product, as shown here, you take two normalized vectors a and b, and their dot product will yield the cosine between them. This is extremely important for lighting, and we'll get more into that into a later video. Another important function to know about vectors is that the length of a vector function returns the magnitude of that vector, and by subtracting two vectors from each other, we get a new vector c, which starts at point B, points towards point A, has a direction from B to A, and has a magnitude equal to the distance from A to B. So in this example, if we were to do vector A minus vector B, we would result in vector C shown above. And if we reverse the order of that and do B minus A, we'll get the same vector pointed in the opposite direction. All right, so congratulations on making it through the vectors overview video. Check out the next tutorial in the series. In the coming video, we're going to be rendering some 3D scenes in Shader Toy with instructions to follow along. See you in the next one.
As you can see, vectors did a lot of heavy lifting there. We use vec3 to mean different things in different contexts. So a vec3 might represent a color where you have a channel for red, green, and blue. A vec3 might represent a three-dimensional point in space, or it could represent kind of a traditional physics vector in the sense that it has magnitude and direction. Perhaps to make it even worse, right? Often you extend into the fourth dimension for different things. Maybe for colors you might need alpha. For points you might want to incorporate perspective or homogeneity. And even in our algorithm, the Raymarching algorithm, our rays are defined as an eye point, a viewer point, and also a direction through the pixel in the screen in the ultimate quest to actually compute a color. Right, so we will use a vec3 type in GLSL to stand for a lot of different things in a lot of different places. And so some of the things that you just saw in that video apply to some of those situations, or are useful in some of those situations, but might not be useful in others. We really do use vec3 to just represent three values, but those three values might mean different things in different places. So try not to let that confuse you. Okay, now it's time for the exciting part. Moving on to Raymarching.
For the sake of this tutorial video series, we're going to be programming on the Shader Toy website in GLSL. It's important to note that GLSL can run in many different environments where OpenGL is supported, and is largely ubiquitous as a tool for graphics processing. To get started, first go to the Shader Toy website at www.shadertoy.com. Log into your account, or if you do not yet have one, create one for free. This will be required for later videos if you want to follow along in this framework. My profile name is Carmen Sandiego, but your profile name will appear here in the upper right-hand corner. Once you've created your account or logged in, click on your profile to view all of your saved marches. In the Shaders tab, all of your saved marches will appear below. So we're going to click on the New tab and create a new shader. For the sake of this demonstration, we're going to show you how to create a scene with a simple sphere that moves around. The first and most essential step to Raymarching on GLSL is setting up a signed distance function for the objects you wish to render. A signed distance function is a mathematical way of describing a shape, and it tells us the closest distance to any vec3 vector in a space, and returns that value. Let's demonstrate what this code might look like for a sphere. All right, so this is the SDF function for a sphere, and it is among the simplest shapes possible. It can be calculated with radius alone. If inside the object, r will be greater than length p, and the function will return a negative value. This tells us how far a point P is from the surface of a sphere with radius r. Unfortunately, a signed distance function alone is not enough to produce output to the screen. We'll need two more steps before we can view any output. First, we will need to employ the Raymarching algorithm introduced in episode 1, the fundamental core of this project. Here's what that looks like. Let's review this code slowly so that we understand how it's operating. This function takes an input of ray origin, which represents a point in three-dimensional space, as well as an input of ray direction, which should be a normalized vector, starting at the camera and pointing in the direction of the ray. At the beginning, total distance is initialized to 0. Inside the for loop, our position along ray is constantly updated in the vec3 variable current position based on how far along we should be traveled, and that's this variable here. After this, the distance to surface is calculated based on our SDF function and returned by the distance value and added to total distance. This step of calculating distance to surface represents the circles which would locate the closest object in our original ray marching model from episode 1. When these circles are too small, we do not continue our ray, but instead break our loop and render this object. In our next video, you'll learn how to modify this function to include several objects in the scene. Now, we only have one more step before you lovely coders will be able to view output for yourselves. We're going to construct a main function responsible for producing output to the screen. Let's see what that might look like. Many of these lines are standard to most every Raymarch. The function itself takes a pixel as an input and outputs a color for that pixel. Next, the vec2 called normalized coordinate ensures that the center of the screen is 0, 0. The variable camera origin sets where the camera begins in space, and ray direction is pointed away from this camera. Then we use our previous perform Raymarch function to compute how far away an object is. If nothing is found, it simply renders the pixel with the chosen background color as default, and the color vec3 variable remains constant. Consider the code on the color variable lines, but know we will consider it much greater detail and expand on it in our lighting video. For now, just understand that if an object is hit, it is colored based on the distance traveled. Once you have this code segment implemented, your program should run a basic render. Feel free to play around with the RGB values in the color initialization to set the background color, or change the second parameter in SDSphere function to affect the radius of the sphere. Let's hit play and view this output. So a little bit faint, but there is a circle right here in the center. Let's learn how to transform our scene further by learning to scale, rotate, and translate objects. What we'll quickly learn in this process is that instead of transforming the object, you simply transform the space around it, which turns out to have identical effects. First, we'll cover translations. How can we move our object in the scene? We're going to modify our signed distance function to allow us to offset its position. So scroll up to your signed distance sphere function towards the top, and we're going to modify it. So all we're doing now is we're going to add another parameter to it called center, and we're going to subtract our point from that to find our new location. Our SDS function now takes the center parameter that will offset along the specified vector. Let's edit this call in our Raymarcher to ensure it's properly rendered. So we're going to go to our Raymarcher, and we're going to change this call in the distance to surface line. So this line we're going to replace. We're going to add a sphere center, and then ensure that sphere center is passed as a parameter to distance to surface. And then this parameter is how you move your sphere center. Well, actually, this is the z direction, so this will move it closer to the screen by 0.5 units. Feel free to change these x, y, or z values and play around with this translation. Scaling an object, particularly a sphere, is much easier than translating it. To edit the size of the sphere, we simply scale the input point by whatever scale factor we desire. This is divided instead of multiplied, as it is inverted. Consider that we are truly editing the scene around the sphere instead of the sphere itself. We're going to modify our signed distance function again to include a float called scale factor. And then we're simply going to divide the point by this scale factor, and this will increase the radius by 1.2. Let's see that in action. So we can see the circle is much larger now. But before we're done, we promised you an extra special little treat. Shader Toy has a unique variable called iTime, which slowly increases as the render runs. If we replace the radius with the sine function of iTime, we can see that as iTime increases, the radius will slowly shrink and grow. This is because sines and cosines are periodic and repeat. This is an easy way to continuously add motion to your scenes. Let's demonstrate the iTime variable in action and have it constantly repositioning our sphere. So we're going to edit our sphere center function to include this new iTime variable. Now, the x and y are both cosine and sine of iTime. So let's see what that periodic motion looks like. Again, it's farther away, so it's blurry, but you can see that the sphere is slowly moving around the screen. All right. Well, if we want to enhance this effect even further, we can also apply a motion to the z-axis. So I'm going to edit this line again, the sphere center. And now I've simply had all of the parameters multiplied by some number, its iTime, and then inside of a sine or a cosine function. So let's hit play on this output. We can see that the sphere bounces around and goes in a circle, fading into the background, and then coming back close enough to be rendered again. Congratulations on making it through the basics of rendering.
All right, at this point you should have your first Raymarch that renders a depth map. So you can see how far away the object is, more or less. One piece of glue that I'd like to give you is to talk about where these SDFs usually live in terms of how the code is structured. So Bryce talked about how he had the SDF for a sphere, and he was using that to kind of render this ball that bounces around, and that's good and fine. Often, though, your scene is placed into a function. It's often called scene or map. So I'll show you map here, and map will have kind of all of your primitives in it. And so when we switch over to the next video, you're going to see that Caleb starts to talk to us kind of from within map, because he's going to tell you about like how do you think about planning out a scene and draw some things together and get things to combine and whatnot. And so the Raymarch algorithm is pretty tight, and it just kind of stays as it is. And then we're going to push on like how do we combine multiple spheres? Like what do we do to make that happen in the upcoming video? So if you see some references to map, just know that this is really just talking about like, hey, we have our SDF functions. We want to kind of put all of these things together into a scene. Maybe you want to render 2 or 3 balls together. Maybe you want to build something cool like you saw in our first videos. And so we're doing that by going through the map function. All right, so I'll let Caleb take it away. Thanks.
Welcome to part 4 of our Raymarch tutorial, where we'll now dive deeper into some of the basic transformations you can use to compose a scene. The most basic of transformations is translation, which we've talked about a little bit in the previous video. Translation allows you to move objects in any of the 3 axes. This is necessary since SDFs are naturally centered at the origin. Although it may come off as contradictory at first, this is accomplished by subtracting a 3-dimensional vector of the desired direction from the original position. You can see this in action here, where I subtract 3 units from the right and it actually moves to the right, rather than moving to the left. The next method of transformation is rotation, which can be accomplished by multiplying 2 of the axes by a 2-dimensional rotation matrix. Since we are working in 3 dimensions, the third omitted axis becomes the axis that we rotate the object around. It is important to pay attention to the order of operations when using translation and rotation, as this can determine whether the object rotates in the new location or revolves around the original location. The 2D rotational matrix can be found here, and the effect in action can be seen here. Now comes the topic of rendering multiple objects. We can render 2 separate objects together by rendering their minimum SDF value, which acts as a sort of union between the 2. This result can be combined repeatedly to allow for as many combined objects as your scene needs. The intersection of objects can be rendered by taking the max of their SDF values. Lastly, you can cut or subtract from an object by taking the max of 1 positive and 1 negative SDF. Here you can see the min function being used, as it takes the minimum value between the 2 objects. We can switch this to max to only show where the 2 items converge. Lastly, we can subtract the box from the ball, which can be seen here. With these basic tools, you can already render a wide variety of scenes. However, there comes an issue of evaluating too many SDFs for your GPU to render smoothly. Luckily, there are a variety of methods that allow you to render multiple objects while only evaluating 1 SDF. First, by taking the absolute value of an object's position, you can create a mirrored version of the object along the mirrored axes at no additional cost. However, you need to subtract an offset so that the mirror is rendered at a separate position from the original. Otherwise, it will appear as nothing happened. So here I've mirrored the position along the x-axis, so we've rendered 2 balls. You can combine these in any direction, or all directions. Finally, you can render infinite copies of an object using the mod function. I say infinite with caution, since it only renders to your max Raymarching depth. At first glance, this may appear to distort the copied image, but this can be fixed by subtracting an offset from the mod function equal to half of the chosen spacing parameter. Fract is a unique case of the modulo function that is equivalent to using the mod function where 1.0 is the second parameter. You can't see it from this angle, but they're actually extending infinitely in the x direction. This can be done in any of the three axes, and even combined just like the absolute value.
All right, Caleb's gotten you through the basics of how you can put some things together, do some intersections and some unions and things like that. He mentioned that he's coloring his image with normals and not to worry about it until later. Normals can be a useful debug tool, but you need those in order to light your objects later and give them material properties. We're doing it mostly numerically in our Raymarchers. There are some places where you can do things analytically. This is an example of the getNormal function. We sample the map in 6 places and find the gradient, which then gives us a vector that points directly away from a surface, and we normalize it so that it has length 1 like we were talking about in the second segment. Down here, we just set our color according to the normal based on how far we've gone. And so we take the ray origin, we add the distance multiplied by the ray direction, and we get the position that we're currently at. And based on the position that we're currently at, we can get a normal from this map as we anticipated. If you are writing this out by hand and not copy pasting it, make sure you get your x, y, y's right. They are setting the offsets to the appropriate values to do the gradient the right way. Okay, Caleb's going to dive in and give us some more pointers into building a scene from scratch. Stay tuned.
We will now use some of these concepts to construct a basic ceiling lamp. You should begin this project with a basic Raymarch setup as explained in our previous videos, as most of this process will only take place within the map function that describes the scene, along with any adjacent functions that we need to create. My version will be colored with the surface normals, but don't worry if that doesn't make much sense yet, as we will go over this in much greater detail in a later video. The SDFs we are going to use will be the box, the cap cylinder, so a normal cylinder with a flat top and bottom, a vertical capsule or a pill-like shape, and a torus ring, all of which can be found on Nico Keelis' site, with link in the description. The exact values will differ depending on your scene setup, but this will demonstrate how a simple scene can be constructed. We will first want to begin by creating 3 cylinders for our bases of our lamp. This will all be done in its own separate function, so we can easily call the whole shape in the map. Lastly, for this part, we'll create a small vertical capsule for the light bulb shaft, and we should have something that looks like this. Now we can construct stabilizers for the frame in another function, and here's where the composition will get interesting. We will create 2 pillars on the side of the light bulb shaft, as well as 4 outer pillars and bars to connect to our yet-to-be-rendered frame. To begin, we'll first create 1 pillar in the center of the composition, and then mirror it along the x-axis using the absolute value trick that we talked about earlier. Now, for the 4 outer pillars, we can do the same thing with another capsule, only this time we'll mirror it along the x and z axes. Finally, we can finish by creating 2 bars aligned with the center base, where one extends outward in the x direction and the other in the z direction. And this will complete our stabilizers to combine with our bases in the map function. Now we can construct the final piece of our lamp, the frame. We will use 2 tori or toruses to construct the top and bottom of the frame. We can reuse the absolute value trick along the y-axis to accomplish this with only 1 torus. Next, we can see subtraction in action by taking 2 cylinders and subtracting the smaller one from the bigger in order to create a shell for the frame. However, we need to make sure that the smaller cylinder is longer than the thicker one, so that we do not get artifacts when rendering their convergences in the center. Lastly, we will take a gyroid fractal to carve out a design of the frame shell. The exact fractal doesn't matter, but it is a quick way to carve intricate designs out of your shapes. I won't go into too much detail for the construction of this gyroid, but I'll include a link to the Art of Code's 2-video series where he dives deep into their construction. And here's the gyroid function. And with that, this will conclude our composition of the lamp. The next video will focus on lighting, where you can add light into the scenario.
Woo! Caleb did a lot of work there. He skipped over how he got some of his SDFs and whatnot, so you can grab them from my fragment shader that's linked down below. Inigo Quiles has a bunch of sign distance functions as well. He mentioned that he grabbed the gyroid shape from Art of Code, but you can grab them from Caleb's work as well. Very cool stuff, and you can see his final product up top, which he hasn't walked you all the way through yet, but the modeling is done for the most part, and so this is what we get. We're just seeing it colored with its normals, so those are vectors that are pointed away. We're treating these vectors as if they're colors. Remember how I told you vector did a lot of work for us? There it is. Okay, the last part is Bryce is going to talk us through some simple shading and how to get some colors from these normals into our renders.
Ever wondered how to create complex, realistic lighting on your 3D renders with nothing more than simple math? Let me show you how to build that from scratch in 5 minutes. It's likely the case that most every time you see a 3D scene, elements of lighting are used to give the objects a touch of realism. To accomplish this, we're going to use a method called Lambertian lighting. This method of lighting is the simplest and is used primarily for matte, plastic, non-reflective, or dull surfaces. It takes into account only the normal of an object's surface and the direction of lighting to determine what color each pixel should be, and is largely considered one of the easiest lighting models. As you'll recall from the vector segment, taking the dot product of two normalized vectors results in the cosine of the angle between them. This property is going to be used directly for lighting. When those two vectors, the surface normal and the light, point in the same direction, the cosine of their angle is 1. When they are at 90 degrees, the cosine is 0, and when they are pointed in opposite directions, it's -1. What this essentially means is that the dot product of two normalized vectors yields a number from -1 to 1, which says how close the two vectors are in angle. In this slide, the surface normal, represented by the blue arrow, always points directly orthogonally away from the surface of the object. The surface normal vector is one of the two used for lighting in the lighting computation. The second is the direction of light, represented by vectors all pointing in the same direction shown here. When all the light comes from a singular point, and all lighting vectors point in different directions based on that light's position, that is considered a positional light. However, when all the light comes from a singular direction, such as in this model, and all lighting vectors have identical directions, this is considered a directional light. The closer the two lighting and normal vectors are, the more directly the light is hitting the surface at any particular point, so it is colored brighter. In other words, the lower the angle between these two vectors, the more light is hitting this section. Now, before we jump into coding, let's examine what this positional versus directional light looks like directly. All right, first, let's examine a positional light. In this model, lighting vectors are entirely dependent on the position of the light which is orbiting this central object. As the light travels closer to the ball, less area is illuminated. This is because the light vectors diffuse in increasing angles as the light gets closer to the ball. The second type of lighting is directional, where all light rays come from the same direction. It's as if there is a light infinitely far away in one direction hitting the object. No matter how close or far the light is to the object, the lighting vector direction stays constant across the entire surface, only changing with direction. A link to this demonstration is attached in the description. Before we start programming, let's introduce one more kind of lighting, Blin-Fong specular. This lighting model functions practically identically to the Lambertian model with an additional specular term in the computation, which we'll cover. For more glossy, shiny, or metal-like surfaces, a Blin-Fong model of lighting can be employed to add glow or reflection, such as in this demonstration. In this example, the positional light traveling between the balls adds a small white glow to the center of the lighting. Now that we understand how lighting works conceptually, let's hop over to Shader Toy. We're going to be building off of our pink ball example from the rendering tutorial section. So here is our pink ball example. So in this first section, we're going to be fulfilling an earlier promise by modifying the color portion of our pink ball render within the main function. Rather than simply coloring based on distance traveled, we are now going to employ Lambertian lighting. So we're going to replace this line. We first make a variable which moves with the center of the sphere, seeing as the sphere moves. Surface variable represents where we are on the sphere, and normalize gets the normal at that point, which is required to calculate Lambertian lighting. This step represents getting the arrow's vectors pointed directly away from the sphere in our modeled example. Light direction represents a consistent point of light in space as 1, 2, 2. Lastly, the diffuse line calculates the dot product of these two vectors and yields the cosine of the angle between them, resulting in the realistic Lambertian lighting that you see. Because cosines can be negative, we take the max of the result and of 0 to create a lower bound of 0. Lastly, we multiply our color by this value. Let's see what this looks like in effect. So we get a much more realistic lighting around this ball. But we're not done yet. We're going to add a blend-Phong lighting effect. And so to add this blend-Phong lighting, used for shiny or metal objects, we first need to calculate a few additional viewing directions. So this line will go right after light direction, where we calculate the view direction and halfway direction. After the diffuse line, we're going to add a specular component, which is calculated as specified. And we're going to replace our color equals line with our new lighting principles. Let's see what this looks like in effect. After we have a handle on these vectors, we can calculate the specular term based on how close the surface normal and half direction are to each other, which is what the dot product is calculating. Surrounding it is a max function to establish our lower bound of 0, just like before, and all raised to the 80th power to give a sharp and shiny look. Lastly, color will be based on a new lighting float value rather than diffuse alone. This lighting float will take into account both the diffuse and specular calculations, mixing them appropriately. And that's what gives this shiny effect. All right, congratulations on making it through the lighting video. Oh, this is the last video in the series, guys. Thank you so much for watching.
All right, so I decided to take the coloring that Bryce was talking about and apply it to the lamp that Caleb had been building and using the colors that he did so that things turn out kind of the same. I added in another extra little term, which I'll talk about here in a second, but you can see here in my code, I define a Lambertian color, I define a specular color, I get the dot product that Bryce was talking about. Here I shift things, instead of using the max and clamping to 0, I shift things so that everything always has a value unless it's pointing directly away from the light. And so this is an effect called ambient lighting, and this is a little hack to kind of incorporate it all into one variable. And so everything's going to get some color. It's just that things that point towards the light will get more color in this situation. And then I just take this dot product, multiply it by the color, and that provides me with some level of color there. If you would like to see what that looks like, it looks like this. You get this kind of pink shading here. And then I get the half vector, which is the normalized vector between the ray direction and the light direction. In this case, the light is at the origin. I'm using a positional light, so wherever I hit, the direction to the light is the opposite of that position, which is an interesting positional vector instance where I take a 3D point in space and I turn that into an actual physics vector because I want a direction that points from there to the origin. I don't know, it's pretty neat. Anyway, so we take that half vector and we do the power in order to get the shiny bits, multiply it by our specular color, which is this cool yellow that's going to give us most of our shading. And so I'll show you just the specular part here. You get this kind of golden with these little highlights in here. You can play around with this exponent here. The bigger the exponent, the kind of tighter this highlight spot will be, and then the smaller the exponent, kind of the wider and brighter, I guess, things will be. And then what you should do is mix them together. And so this was actually a little bit of a bug in Bryce's tutorial here, where he had his mix value in the middle and it was like 1.2 or something. I wouldn't do that. A mix as something like this probably makes sense. Another thing that will often happen is instead of doing a mix, what they'll do is they'll add the colors together. And this may be a direct add or it may be a fractional add. So like if you want the surface to be 50% dull, and then you want it to be like 50% shiny, then you might like fractionally add these together. And if you compare this result here with the mix result, they are different. If I give specular a little more and diffuse a little less, then this should be exactly what mix is doing. And so you can kind of tailor this to taste. If you wanted to give kind of a mix of these things, you can. If you want to actually mix them yourself, you can as well. Okay, well, that's going to end our six segment. I guess we're at 6 segments. Our 6 segment tutorial series. I hope you learned something about Raymarching. I hope you learned something about computer graphics. I hope this inspires you to like try some things out. Make some cool stuff. All right, well, that's it for the tutorial stuff. We actually did a lot more stuff this summer, including shadows, soft shadows, reflections, refractions, Fresnel equations, all kinds of stuff. Hopefully this inspires you to dig at some of that stuff too. Maybe make some art, maybe model something on your own, make a game, or whatever. But that's it for us for this particular summer. Maybe I'll be back and do some more if this is something that you all enjoy. Remember to take care of each other, and in order to do that, you have to take care of yourself. We'll see you.